Okay, so should have this up already. We are going to look at sort of using this Sturm-Liouville stuff to analyze/solve a certain problem. So this is what it's going to be. We're going to look at the problem 1 plus x times the x derivative of u, sorry, not the x derivative, the t derivative of u is equal to the x derivative of 1 plus x squared times the x derivative of u. Okay, so this represents some sort of heat or diffusion equation where the mass is 1 plus x, for example, where the mass density or the specific heat times the mass density is 1 plus x, and then 1 plus x squared would be like the diffusion coefficient. And then we're going to give this Neumann condition, so the x derivative at 0 is equal to the x derivative at 1, and they're both equal to 0. So this corresponds to where the ends of the rod are going to be insulated if we're thinking about this modeling temperature in a rod. And then this initial condition, u of x 0 equals 1 minus x squared. Okay, so now we want to try to use Sturm-Liouville theory to the extent that we can to analyze this problem. Now, there's going to be one big step that we don't do, and I'll explain what that means, though maybe you kind of understand what it is already. So I want to come up with the corresponding eigenvalue, eigenfunction problem. So the operator is going to come from the right-hand side. So I'm going to define an operator, L phi is going to be equal to 1 plus x squared times phi prime, and I'm doing the derivative of all of that. And then my eigenvalue, eigenfunction is going to be L phi is equal to minus lambda times 1 plus x, that's the coefficient there, times phi, and then I have the boundary conditions. I don't know if you can see it, I'll step out of the way in a minute. Phi prime of 0, phi prime of 1, and they're both equal to 0. Okay. And I know, based on the Sturm-Liouville theory, here sigma is 1 plus x. That is continuous and strictly positive. P is 1 plus x squared. That is continuous and strictly positive. And I have these conditions here, which correspond to beta 1 and beta 3 being equal to 0, and beta 2 and beta 4 being equal to 1, or any non-zero number. And so I know by the Sturm-Liouville theory, I've got a sequence of eigenfunctions, which I will call lambda k, and eigenvalues lambda k, and eigenfunctions phi k. And these eigenvalues and eigenfunctions satisfy a few properties here. I know that L times phi k is equal to minus lambda k, 1 plus x phi k. That's just what it means to be an eigenvalue and eigenfunction. And I know if I do the integral from 0 to 1 of phi k, phi j, 1 plus x. The 1 plus x comes from the sigma here, that this is equal to 1 if k is equal to j, and it's equal to 0 if k does not equal to j. Okay, so now I want to use this to write the solution. So using the eigenfunction expansion, I'm going to have u of xt is equal to the sum k equals 1 to infinity. Now any function I can write in this way, uk of t times phi k of x, and I can choose my ck's of t. For every t I get a different function, and I can do this in such a way that this series is going to converge to u of xt, where u of x is continuous, and otherwise it'll converge to the average of the two. If there's a jump discontinuity, it'll converge to the average of the left and the right. Okay, now this is true for any function. In particular, I can now take derivatives. So if I plug this into the right-hand side of the equation, in other words, I have the x derivative of 1 plus x squared times the x derivative of u. Well, the way that this is going to hit the sum here is it's only going to mess with the phi k's here, because it's x differentiation, so it's not going to do anything to the t's. So what this is going to be then is the sum k equals 1 to infinity ck of t times L phi k of x. Because that's what, if you do this just to the x variable, you get exactly L phi. That's why we defined it that way. Okay, well, what is L phi? Well, this is minus L phi k is minus lambda k phi k of x, times 1 plus x. So this is the sum, so minus the sum ck of t, lambda k times 1 plus x phi k of x. Now on the left-hand side, if we do 1 plus x times the t derivative of u, this is going to come to the sum the following way. K equals 1 to infinity ck prime of t 1 plus x phi k of x. Now the phi k's are orthogonal and therefore linearly independent. So what this means then is that if these two functions are equal to each other, it means the corresponding coefficients are equal to each other. So so this is true, this equality is true, and this equality is true no matter what we know about u. Okay, but if we want u to satisfy the PDE, then they must be equal to each other. And if they're equal to each other, since the phi k's are orthogonal and therefore linearly independent, the corresponding coefficients must equal to each other. In other words, this is equal to this, and along with the minus sign. Well, there's a 1 plus x, so I can cancel that out, and we get ck prime is equal to minus lambda k ck. Therefore, ck of t is equal to ck of 0 e to the minus lambda k t. It's just solving an ordinary differential equation. And because we know that because we know that phi k satisfy these orthogonality conditions, as we saw in previous lectures, ck of 0 is just going to be equal to the integral from 0 to 1, the initial condition, which is 1 minus x squared, times phi k of x times 1 plus x dx. Okay, so I'm going to write that up here. So I'm just going to kind of copy and paste this little by little, or maybe not little by little, but just in a couple of steps. Okay, so we've got this sum, k equals 1 to infinity. Now ck of t is ck of 0 times e to the minus lambda kt, and they're going to multiply this by phi k of x. And now we're going to take our expression for ck of 0, but I'm going to use y as the variable of integration. And so we're going to get the sum, k equals 1 to infinity, ck of 0 is the integral from 0 to 1 minus y squared, phi k of y times 1 plus y dy, and then times everything else. So we're going to get e to the minus lambda k t phi k of x. Okay, so the quantity in brackets here is ck of 0. This is also ck of 0. I'm just using y as my variable of integration. Okay, now I'm going to interchange the summation and integration, which I can do. And I'm going to get the integral from 0 to 1 of 1 minus y squared. Remember, that comes from the initial condition here. And then times this sum, which is the sum k equals 1 to infinity, e to the minus lambda k t phi k of x phi k of y, and then times this 1 plus y. So I want to put this in, I want to put the sum in a bracket, times 1 plus y dy. Okay, now this function right here is going to be very important. We'll see going throughout this week that's going to be something called Green's function, which we will talk about, like I said. We'll talk about it this week, but this is how we can write this. Now, the big part that we haven't done yet is we haven't actually solved this differential equation. We haven't solved L phi equals minus lambda 1 plus x phi to find like an actual formula for the eigenvalues and eigenvectors. Now, there's a huge sort of area of math called special functions, which deals with second-order differential, which essentially deals with second-order differential equations like this, and finding properties of those functions. And so if you look at things like Bessel functions, this is an example of you take some second-order differential equation that comes up a lot, or a second-order differential equation that you can sort of convert other equations into, and you solve that, you get information, asymptotics, whatever, about those functions, and then you can apply the theory. You can take that information about the functions, plug it in here, and answer the different questions that you might be interested in answering. We're not going to get into that class, and we're not going to get into that in this class, but I just wanted to point that out, that yes, like in terms of practicality, we still don't know what lambda k's and phi k's are, but this gives us a way to explicitly write out, at least in some sense, explicitly write out solutions to these problems. And then if you can figure out information about the phi k's and lambda k's and stuff like that, you can discern other pieces of information as well. Okay, that's it for this problem.